All right, let's get right into it. Today, we're digging into a really fascinating note from a physicist named E.T. Jaynes, and tucked away inside is this idea, a consequence of thermodynamics that's so wild, it basically suggests we have been heating our homes completely wrong this whole time. So let's see what this is all about.
I mean, really think about that for a second. What if you could slash your heating bill by a factor of 8? This isn't just some hypothetical question. What if almost everything you spend on heat isn't just a necessary cost, but actually a sign of this massive, hidden potential we're not even touching? It sounds like something out of science fiction, but according to Jaynes, it's really just better physics.
And there is the number, 8.66 times more heat from the exact same amount of fuel. Now, this is not a magic free energy trick or anything like that. This is the absolute theoretical maximum you could get, and it's calculated straight from the laws of thermodynamics in a really common situation. So how in the world do we get there? Well, first, we kind of have to understand what we're doing right now. So the way we all heat our homes and buildings right now is, frankly, from a physics perspective, just unbelievably wasteful. We're using a sledgehammer to crack a nut, and we don't even seem to realize it.
Think about what's actually happening in your furnace. You've got this flame that's burning at 1,000 degrees, maybe more. That's incredibly high-quality, high-temperature heat. But what do we actually want? Just a comfortable room, maybe 25 degrees Celsius? By just letting that super high-quality heat degrade down to that low temperature, it's kind of like having a giant, powerful waterfall and using its incredible force just to get your hands a little wet. We're throwing away almost all of its potential.
In the world of physics, this is what's known as an irreversible process. When you let heat just flow directly from a hot source to a cold one like that, the total entropy, you can think of it as disorder in the universe, goes up. And that increase isn't just a number, it's a physical measurement of wasted opportunity. It's a flashing sign that says we could have done something really useful with that temperature difference, but we didn't. Okay, so if direct burning is the lazy brute force method, what's the smarter, more elegant way? Well, Jaynes lays out this beautiful two-step process that actually works with the laws of thermodynamics to get these incredible results.
And this really lays it out perfectly. On the left, that's us now. You burn 1 unit of fuel, and in a perfect world, not even counting what's lost up the chimney, you get 1 unit of heat in your room. It's simple, yeah? But it's really inefficient. Now, look at the right, the smart method. You burn that same single unit of fuel and you get many units of heat into your room. So the big question is, how is that even possible?
And here it is. This is the elegant solution. Instead of just letting that super hot flame's heat spill into your room, you first use it to run a heat engine. The engine takes that temperature difference and creates useful work, like electricity. Then, and this is the key, you use that work to power a heat pump. A heat pump doesn't create heat, it just moves it. It literally grabs the free heat that's already in the cold air outside and pumps it indoors. And the best part? The so-called waste heat that the engine gives off while doing all this work, that gets used to warm the room too. Nothing is wasted. It's just a beautiful, cascading use of energy.
Okay, so let's get into the actual numbers. Because when you run the math on this for a typical winter day, the results are, well, they're just staggering.
So Jaynes sets up a really simple example. Let's say your furnace flame is at 1,000 Kelvin. You want your room to be a cozy 25 degrees Celsius, which is 298 Kelvin. And let's say outside it's freezing, 0 degrees Celsius, or 273 Kelvin. Believe it or not, those are the only 3 temperatures you need to figure out the absolute maximum possible heating efficiency.
And there's the payoff. With direct heating, you get 100% of the fuel's energy as heat, at best. But with this thermodynamic method, 866%. That's the 8.66 number we saw before. Over 8 times more heat for the same fuel. And why? Because most of the heat warming your room wasn't created by burning fuel. It was just moved from the outside for free. The fuel was just the ticket price to power the machine that does the moving. And this isn't some weird fluke that only works at exactly 0 degrees. The paper actually includes a chart that shows this is a general principle. In fact, the closer the outside temperature is to your room temperature, the more ridiculously efficient the whole process gets. Even in really cold climates, average gains of around 5 times are, in theory, totally possible. As if completely upending how we think about heating wasn't enough, Jaynes then uses this exact same logic to come up with something even more mind-bending. He calls it the free oven.
I mean, that just sounds impossible, doesn't it?
How could a freezing cold day possibly help you bake something? It feels like it breaks our intuition, maybe even the second law of thermodynamics that says heat flows from hot to cold. But it doesn't.
It's the exact same principle, just running in a different direction. You use the temperature difference between your warm room and the even colder air outside to run an engine. That engine's work powers a heat pump, but this time the pump takes heat from your room and concentrates it into a small insulated box, an oven, making it much, much hotter. And get this, the colder it is outside, the bigger the temperature difference and the more efficiently the whole thing works. The punchline? When you're done, you can theoretically reverse the process, put the heat back in the room, and restore everything. The net operating cost is zero.
And that really brings us to the most powerful takeaway, and it comes from Janes himself. This isn't science fiction. It's not some loophole in the laws of physics. It is the laws of physics. The only thing standing between us and this kind of incredible efficiency is engineering. The science is solid, the path is there, it just needs someone to build it.
Janes actually writes that the person who figures this out and makes it a reality will be one of the world's great benefactors. It really makes you wonder, doesn't it? If this incredible potential for efficiency is just sitting there, written right into the laws of nature, what other amazing opportunities are we overlooking every single day?